Hello my dear students, welcome back to the second session on surface chemistry. Last class we had learnt about the difference between adsorption and absorption, and also we learnt about types of adsorption. Today we are going to learn about what is adsorption isotherm and also about the new concept catalysis. So we will see what is adsorption isotherm. What do you mean by adsorption isotherm? It is a graph in which you can see the variation of adsorption, or I can tell extent of adsorption versus pressure at constant temperature. That is, the entire adsorption process, when it is happening, we are keeping the temperature constant. To explain this more easily or to make it more clear for you all, I'll just take an example in which I'm taking a container. Okay, I've placed an adsorbent, I've taken some gases, and this is fitted with the piston, and the entire system temperature is kept constant. Now there is adsorption which is happening. Okay. Now if the pressure increases, for physical adsorption of course, if the pressure increases, the extent of adsorption or the adsorption process also increases. The pressure increases, even the adsorption process also increases when temperature is kept constant. Now if we are taking the extent of adsorption, okay, I'll explain what is x by m. If I am taking extent of adsorption and pressure, and if I am plotting a graph, I am going to get the curve, and this is called as adsorption isotherm curve. Now Freundlich in 1909 also gave a mathematical expression for adsorption isotherm, and that expression goes like this: x by m is equal to k into p to the power 1 by n. Now what does x by m mean? Okay, that is, x is mass of the gas adsorbed, and what is m? It is mass of the adsorbent. Okay, and what is k and n? It is constants, which can again vary when the temperature is varied. Okay, and p means pressure. Now here you can see he is given the variation. This x by m is also called as extent of adsorption. That is, the mass of the gas adsorbed by mass of the adsorbent is also called as extent of adsorption. You can understand by the value of x by m, you can understand whether the adsorption is increasing or decreasing. Okay, so we also call it as extent of adsorption. Now if you see the definition, he gave an equation. What does it represent? Isothermal variation of adsorption. Isothermal means again temperature is kept constant, of adsorption of quantity of gas adsorbed by unit mass of a solid with pressure. So he has taken the variation of extent of adsorption with the pressure, keeping the temperature constant. When the graph was plotted for extent of adsorption and pressure, okay, pressure is taken in x-axis, x by m is taken in the y-axis. You can see at different temperatures there was a curve which we got. Now what do you understand from this graph? Okay, so first thing we shall take now from here up to this portion, okay, and I will put it as A. You just observe this line. It is almost a straight line. It is almost a straight line. From this we understand that extent of adsorption, that is x by m, is directly proportional to P, that is pressure. That means when the pressure is increased, adsorption process also increased. So x by m is almost directly proportional to pressure. That means 1 by n is equal to 1. It is almost is equal to 1. That's the reason 1 by n is equal to 1. Now, if you observe after this point in the curve, okay, I'll take this point as B, this point. If you see, if I just give an extension of these graphs, it's almost a straight line. It is almost a straight line. That means how much ever I am going to increase the pressure, extent of adsorption is not increasing, or the adsorption process is not increasing at all. Here x by m is equal to constant. That means 1 by n is equal to 0. Now 1 by n, when it becomes is equal to 0, if you put in that formula, you can see it is x by m is equal to k p to the power 0, that is 1. So x by m will be equal to constant. That is the point, or after this, the pressure after this is called as saturation pressure. It is called as saturation pressure. Already the adsorbent, what is there, it has come up to the saturation level. If you are increasing the pressure also, there is no adsorption taking place. The extent of adsorption becomes constant. Okay. Here is the place where Freundlich couldn't explain the process of adsorption, or he couldn't explain the isotherm at high pressure, where after the saturation he could not explain it better. Now, if you see from the point A to B, here is the exact pressure variation. You can see the extent of adsorption where you are going to get a curve. Okay, and probable value of 1 by n should be somewhere between 0.1 to 0.5. The probable value will be 0.1 to 0.5. So that is what you are going to understand from this graph. That is, at a lower pressure, it is almost extent of adsorption is directly proportional to the pressure. At a very high pressure, the adsorption will come up to a saturation level. Okay. Next, also if you see this graph, as the temperature is increasing, you can see the adsorption, the extent of adsorption also is decreasing. Yes or no? See, at 195 Kelvin, you can see extent of adsorption was at a higher pressure was up to here. Okay, whereas at 244 Kelvin, the extent of adsorption, you can see there is a drastic change. It's from here up to here. Yes or no? At some more higher temperature, you can see it is still reduced. That means as the temperature is increased, the extent of adsorption has been decreasing. There's one more thing which you can understand by looking into this graph. Now, to understand the validity, whether this Freundlich isotherm is valid for the particular experiment, how do you understand that? For that, what we do is, we take the formula, okay, x by m is equal to k p to the power 1 by n. Okay, we apply log for this, you will get log x by m. Now it is a multiplication. When I put log, it will become addition, that is log a into b is log a plus b. So log k plus log p to the power 1 by n. Now log a to the power b, I will writing as b log a. That's the reason I have written 1 by n log p. I hope you remember this from your first year. So if I apply log for the expression given by Freundlich, I will get this particular expression or formula. Now if I compare it with y is equal to mx plus c, It is a straight line equation, correct? And if I plot a graph, I have to get a straight line. If I am not getting a straight line, then the Freundlich isotherm expression for that particular experiment is not valid. That's how you validate it. Take this and draw the graph value, that is log x by m I take on the y axis, log p I take it on the x axis. I should be getting a straight line in which intercept is log k, okay, and the slope will be equal to 1 by n. If we do not get a straight line, okay, if it is a straight line, the Freundlich isotherm is valid, otherwise Freundlich isotherm is not valid, okay. That's how you validate for the Freundlich isotherm expression. I hope you have understood about this. The next one is adsorption from solution phase. Now what happens? This was from the gaseous phase. What did we consider? I took an adsorbent and I considered the gas which was there, and physical adsorption we had considered for Freundlich isotherm, which I had explained. Now we will see in the solution phase also whether it is applicable, okay. Now for example, we have taken acetic acid, okay. I have taken acetic acid solution and I have added the activated charcoal. I have taken what? Acetic acid is mixed with water, so I am telling it as acetic acid solution, with water it is there, and I have taken activated charcoal. Initially, before adding activated charcoal, the concentration of acetic acid was high. After adding activated charcoal, the acetic acid concentration reduced. That is because of adsorption process. Correct? Due to adsorption, what happened? The concentration of acetic acid reduced. That is, the particles of acetic acid got adsorbed on the surface of the activated charcoal. That's why the solution concentration of acetic acid reduced. So this is the example which we are taking. When this experiment was done, such experiment was done, this is just an example, okay. They observed several things. What was that? They have done many experiments, and in the solution phase there are certain observations which was done. That is, first thing, decrease in increase with temperature. That means the extent of adsorption decreased when the temperature was increased. The adsorption decreased when the temperature was increased, okay. The second observation which was made was increase with an increase in surface area of the adsorbent. That means the adsorption, if I add more activated charcoal, that means I am giving more surface area. When I have given more surface area, the adsorption process increased. That is, when the surface area or the adsorbent quantity was increased or the surface area was increased, the adsorption process also increased, or the extent of adsorption also increased. That's the second observation which they did. Third one, the adsorption process depends on concentration of the solute. If the concentration of the solute, here in this example, what is the solute? Acetic acid. If the concentration of acetic acid was high, the adsorption process also increased. If the concentration of acetic acid only is low, then the adsorption will not be very fast. It will be a little slower, okay. So that is the third observation which was done. The fourth observation is depends on, that is the adsorption depends on nature of adsorbent and the adsorbate. Maybe some of the acids, it was observed that some of the acids or some of the solute particles did not get adsorbed at all on activated charcoal. So what is the adsorbate and what is the adsorbent? There the process of adsorption should happen. Okay, you should be very careful what is the adsorbate and what is the adsorbent which we are using. The adsorption process also depends on nature of the adsorbate and the adsorbent. So these were the observations which was done. Again, we shall just revise. What is it? When the temperature was increased, the adsorption process decreased. The surface area of the adsorbent was increased, the adsorption increased. It also depends on the concentration of the solute in the solution. And the adsorption also depends on nature of the adsorbent and the adsorbate. Okay, so these are the observations which was done in adsorption in the solution phase. Now for this also they have applied Freundlich isotherm. Here instead of pressure we are writing concentration. X by m is equal to K C to the power 1 by N. X is again mass of the solute which is adsorbed. Okay, X is mass of the solute which is adsorbed. M is the mass of the adsorbent and C is the concentration of the solution. K and N are the constants. Now what happens when I apply log to this? I'll get log x by m is equal to log k plus 1 by n log c. Now for this again, if you see, it is just like a equation for straight line. If I draw the graph for this, okay, how do I draw the graph? I am taking log x by m on my y axis, y log x by m, then log c on the x axis. Okay, I should be getting a straight line in which the intercept will be equal to log k and the slope, if I calculate the slope, it will be equal to 1 by n. So Freundlich isotherm also you can apply here to the adsorption in the solution phase. I hope you have understood about the isotherms. Okay. Next, moving forward, we shall see some of the applications of adsorption. First one is production of high vacuum. If you have to get high vacuum, all trace amounts of gas has to be removed, then we can use activated charcoal for this. Okay. The second application is in gas mask. If the gas mask contains again activated charcoal where it can adsorb any poisonous gas which is there in the surrounding. So in gas mask also again adsorption is the process which is applied. Next, controlling humidity. For example, we can use even silica gel which can adsorb the moisture and control the humidity. Okay. Next is removing of coloring matter from the solution. Last class I had already explained with methyl blue. Same way, for example, if you want to decolorize sugar, the sugar which we have, it is white color, but exactly the sugar which we get from sugar cane, that is, it is a little brownish. For that decolorization from that brown to white, okay, we actually use animal charcoal or activated charcoal. Okay, so removal of any coloring matter, again the principle there behind that is adsorption. Next is heterogeneous catalysis. I shall be explaining this further in the same class. Next, froth flotation process. Froth flotation is a process which is used in concentration of the ore. Okay, concentration of the ore for extraction of the metal. You will be learning this in one of the chapters for your second PUC. So, we will learn about this detail in your particular chapter. Next is adsorption indicators. For example, when we do titration, some of the indicators used are based on the principle of adsorption, where you can see the color change at the end point. So, that is adsorption indicators. Last is in chromatographic analysis, that is, it can be paper chromatography or column chromatography. The main principle is adsorption there, where you are using these chromatographic methods to actually separate the constituents which is there in the mixture. So that is chromatographic analysis. So these are the applications of adsorption. You may have to remember 3 or 4 if it is asked for 2-mark question. Next one, new concept, that is catalysis. You have heard about this word catalyst. We have also learned some of the reaction in which we are writing a catalyst is used. Okay, For example, in your first year you learnt the catalyst which was used in Wood's reaction, okay. Then you learnt the catalyst which is used in hydrogenation or reduction reaction in alkenes and alkynes. Yes. So what is catalysis, or what is a catalyst? A catalyst is a substance which alters the rate of the reaction, means it will increase or decrease the rate of the reaction without themselves undergoing any change. Then we call them as a catalyst. Itself will not undergo any change, especially chemically and quantitatively. That means the quantity what you have added, and chemically that catalyst will remain as it is throughout the reaction. For example, if I have added 1 gram of the catalyst for a reaction, it's just an example. After the reaction also you will have that 1 gram of the catalyst as it is. Okay, it just alters the rate of the reaction. That means by adding a catalyst only you can increase or decrease the speed of the reaction or the rate of the reaction. Such a substance we call it as a catalyst. Okay, so the definition goes like this: substance which alters the rate of a chemical reaction without changing themselves chemically or quantitatively after the reaction is called catalyst, and the phenomena is called as catalysis. There are two types of catalyst, that is positive catalyst which increases the rate of reaction, and negative catalyst which decreases the rate of reaction. Now for example, if I use potassium chlorate KClO3 and heat this, I will get potassium chloride and oxygen. Okay, I'll just balance this. Okay, now when I heat it just like that without using any catalyst, we require a temperature above 653. Okay, we require a very high temperature. But for the same reaction, if I am using MnO2, manganese dioxide, as a catalyst with a very lower temperature only, the reaction or the decomposition of potassium chlorate is possible. That means the speed of the reaction also increased at a little lower temperature, like 270 degrees Celsius only. The reaction actually happened instead of 650 Kelvin temperature. Okay, so this is a positive catalyst. What did it do? It increased the rate of the reaction. It increased the rate of the reaction, that is decomposition of potassium chlorate became faster when manganese dioxide was added. So it is a positive catalyst. Now some of the reactions, for example, if we take chloroform, okay, chloroform, if it comes in contact with oxygen, okay, that is air, oxygen, in the presence of sunlight, it can form a poisonous gas called as phosgene. Okay, now to reduce the rate, we don't want that phosgene to be formed. I want to reduce the rate of the reaction. Okay, at that point alcohol is added so that the rate of the reaction is decreased and the phosgene will not be formed. So when we store chloroform, what we do is we have to keep it in dark colored bottles, filling it up to the brim so that there is no air. Also, small amount of alcohol is added so that chloroform, even when it comes in contact with air and sunlight, the process of formation of phosgene will be reduced, or the rate or the speed of the reaction will be reduced. This is an example for negative catalyst. Okay. Now catalysis can be broadly classified into two types: homogeneous catalysis and heterogeneous catalysis. What is it? Homogeneous catalysis and heterogeneous catalysis. Let's see what it is. First one, homogeneous catalysis. Homogeneous catalysis is where the reactants, products and the catalyst are all in the same phase. Same phase means solution, or it should be in solid or in the gaseous phase. You can see here sulfur dioxide is a gas, oxygen is a gas, nitric oxide is a gas, sulfur trioxide is also a gas. So you can see the reactant product as well as the catalyst, it is in the gaseous phase. So such type of a reaction is an example for homogeneous catalysis. Okay, here one more example you can see, where you can see here it's liquid phase. Here aqueous means it's again in the solution phase itself, and even the catalyst which is used is in the liquid phase. So this is an example again for homogeneous catalysis. You can remember any one of the examples. Next is heterogeneous catalysis. If the catalyst and the reactants products, okay, especially the reactants and products you don't have to bother too much, it is about the reactants and the catalyst. Okay, if the reactants and the catalyst are in a different phase, then we call it as heterogeneous catalysis. Here you can see sulfur dioxide giving sulfur trioxide gas, we are using a solid catalyst platinum. We are using a solid catalyst platinum. It is in the solid phase, whereas the reactant is in the gaseous phase. So there is a change in phase. Such reactions is an example for heterogeneous catalysis. Again one more example, this is for Haber's process, that is nitrogen, hydrogen giving ammonia in the presence of iron as a catalyst. Iron is a solid, whereas nitrogen and hydrogen are gases. So this is an example again for heterogeneous catalysis. Hetero, different, homo means it is same. Okay, so that is two types of catalyst. Next we have, this is the adsorption theory of heterogeneous catalysis. The entire heterogeneous catalysis happens basically in 5 steps. Okay, that is, first you have the catalytic surface having free valencies. Okay, these are the free valencies which is shown. Now let me consider A and B are the reacting molecules. The first step will be diffusion of the reactant molecules towards the catalyst. That means the reactant molecule should come towards the catalyst. That is the first step. Second step, adsorption of the reacting molecules. Now you can see here A and B are adsorbed next to one another on the surface of the catalyst. Third step is reactant should react with one another, okay, and an intermediate is formed. Okay. The fourth step is desorption of the product molecules. AB is the product, it will get dissolved or it will get removed from the surface of the catalyst. And the fifth step is diffusion of the product away from the catalyst so that a new reactant can come and get adsorbed, or it can make space for the new reactants to come and get adsorbed. So these are the 5 steps for in adsorption theory of heterogeneous catalysis. So I shall repeat. First, the reacting molecules will diffuse towards the catalytic surface. Second, adsorption of the reactant on the catalyst surface. Then reactants on the surface to form an intermediate. Then desorption of the products, that is removal of the product from the catalytic surface. And the fifth step is diffusion of the products away from the catalyst so that it can make space for the new reactants to get adsorbed. Okay, so this happens continuously in adsorption theory of heterogeneous catalysis. Okay, I hope you have understood. Next is features of solid catalyst. Okay, next is features of solid catalyst. Now what is the feature which is more important, or what is the most important for a catalyst? First is activity. A catalyst should make the surface available for the reactant molecules to get adsorbed, and it should get adsorbed or it should form the bond in such a way that it is not very strong. Okay, the bond between the catalyst and the reactant should not be very strong, it should be moderate so that once the reactant react, they can get dissolved very easily or they can be broken very easily. If the bond between the catalyst and the reactant becomes very strong, then the surface will not be available for the new reactants to come and get adsorbed. Okay, so that is called as activity of the catalyst. The activity of the catalyst, that is the bond which is formed between the catalyst and the reactant molecule, should not be very strong. That is the first feature. Okay, that is activity. Second is selectivity. What do you mean by selectivity? The selectivity of a catalyst is ability to direct a reaction to yield a particular product. That means a catalyst can direct the reactants and tell which are the products to be formed. For example, I will just explain with an example. You can see here carbon monoxide and hydrogen. All the three reactions, the reactants are same. It is carbon monoxide and hydrogen. Here also carbon monoxide and hydrogen, carbon monoxide and hydrogen. What is changing is only the catalyst which we have used. Here we have used Ni, nickel. Here along with copper we have used zinc oxide with chromic oxide, and here again we have used only copper as the catalyst. As the catalyst changed, you can see the product also changed. First one, carbon monoxide with hydrogen, we got methane and water. Second one, carbon monoxide with hydrogen, we got methanol, CH3OH, and carbon monoxide and hydrogen, I got formaldehyde, HCHO. Okay, so what happened? I got three different products when three different catalysts was used, but the reactants are exactly the same. So this is called as selectivity of a catalyst. It's an ability of a catalyst to direct the reaction to yield a particular product. It can direct the entire reaction to get a particular product. That is called as selectivity of a catalyst. I hope you have understood. Next one, we learn what is zeolites or shape selective catalysis by zeolites. This also is shape selective catalysis. Now what are zeolites? They are very porous type of a catalyst which are very selective to the shape. Now shape of what? It is the shape of the reactant, shape of the product. Also the reaction depends on shape and size of the zeolite pore and cavities also. Okay, so what do you mean by shape selective catalysis or zeolites? It is the catalytic reaction that depends upon the pore structure of catalyst and the size of the reactant and product. What is the pore structure of the catalyst? Okay, what is the pore structure of the catalyst and what is the size of the reactant, the product? Such type of catalytic reactions we can see in zeolites or shape selective catalysis. Okay. Now, zeolites are good example here I told because of their honeycomb like structure. You can see like honeycomb. In honeycomb there are depression or cavities which is there. Same way you can see in zeolites also. They have got honeycomb like structure. Now what happens here is there is a particular pore size for a zeolite. The reactant will come and get attached here. Okay, or the reactant can move inside. As they are going, because of the depressions in the cavity, the cracking can happen and you will get the product. The product will be the smaller in size so that it can come out very easily, and the reactant will be exact size where it can fit into the cavity. Okay, I hope you understand. The reactant will be fitting into the cavity or it can just go into the cavity or the pore, and the product will be smaller in size so that it can come out very easily. It is usually that's happening in ZSM 5, which is a catalyst which is used for conversion of alcohols into petrol, okay, or gasoline I can tell. Okay, ZSM 5, where alcohol is directly converted into our gasoline. Okay, this is one of the example or one of the types of zeolites. In zeolites contains such framework, that is aluminum oxygen silicon framework. Okay, you can see aluminum oxygen silicon, again aluminum oxygen silicon framework is there. Some of the silicons, actually instead of aluminum it should have been silicon, but it is replaced, silicon atoms have been replaced with aluminum to get such framework in zeolite, so that they get a particular type of pore and the reaction can happen. So the entire reaction depends on the size and shape of the pores and the cavities of zeolites and the size and shape of the reactants and the products. That's why we call it as shape selective catalysis. I hope you have understood. Okay. So in catalyst, what are the concepts which we learned? What is a catalyst? What is a positive catalyst? What is a negative catalyst? Then you learnt about homogeneous catalysis, heterogeneous catalysis. Then you learnt about the adsorption theory in heterogeneous catalysis. Then you have learnt about the features of solid catalyst, that is activity and selectivity. Also we learned shape selective catalysis by zeolites. Okay. So there are some more topics which we will learn in the next class, that is enzyme catalysis we will learn in the next class, and also a new concept, colloids and types of colloids, I shall be covering in my next session. So hope you have understood the concept today. Stay tuned, stay focused. Thank you my dear children.